Hello, and welcome to week 8, Regression Methods. My name's Elias, and I'll be your lecturer for the next 3 weeks. This week we're covering regression methods. Next week will be neural networks, and then the week after that will be convolutional neural networks. So just a little bit of an overview of what we're going to talk about today. First, we're going to introduce a modular approach to thinking about machine learning that we're going to be building upon and using over the next couple of weeks. We're going to be talking about what a model is and how it defines basically the relationship that you're assuming your input variables and output variables have. We're going to be talking about loss. Loss functions measure how good a prediction is. We're going to be talking about regularization next week, so stay tuned for that. And then today we're also going to be talking about gradient descent, which is how a model learns. After that, we're going to expand on linear regression. We're going to show some multivariate linear regression. We're going to show polynomial regression. Then we're going to show logistic regression. Okay, first, so what is a model? I mean, we hear what a model, we hear this term thrown around in machine learning a lot, but let's really concretely talk about what a model is. So a quick definition for a model is that a model is a function that maps input features to a target value. In this lesson, we're going to define a model based on its weights or parameters. More on those terms soon. And those parameters / weights scale different input dimensions. That's why they're called weights. So in this thing here, we have x, right? And those are our inputs. X is bold because x could be a vector, meaning we have multiple input variables. Y is our prediction. And a model is good when its prediction matches the target or approximates the target, right? We want it to approximate the target. And models in machine learning specifically, we train them, right? So we don't define a model ourselves. It's not like we're writing down a function saying like f of x equals to x plus 3, right? We're not doing that. We are basically telling our machine, hey, here's a bunch of data points. Can you learn what function approximates these the best? Training is also called fitting a model to our training data. Yeah, you might hear like fitting a line to our data, stuff like that. And what's happening during training or fitting is the parameters / weights are learned, right? So basically our idea is we're going to go from maybe some random initialization. So in this case, we're looking at a line. We're going from some random, say like initialization like this, and we're learning it and we're getting better. So maybe it'll like shift down to here and we'll get better. And this looks like the best line. So we're learning a line, and the line can be represented as mx plus b in linear regression. And here our two parameters would be m and b, right? Because these are the things that define our line. If this seems confusing right now, don't worry, we're going to be talking a lot about this today. So what is linear regression? So linear regression is a type of model. And it's a model that assumes that the underlying relationship between your input and your output is a line, right? Linear line. That makes sense. It also can be in higher dimensions other than just single dimension. So if you look over here, that's a line, right? We have one input dimension and we have one output dimension, right? And that is a one-dimensional line in two-dimensional space. If we want more than one input dimension, so we're adding more data input into our model, higher input dimensional space, we could have something like a plane, right? So here we have two input dimensions, two input features. I'm going to be using those interchangeably, and then one output, right? So that is a two-dimensional plane in 3D space. Make sure that you can see how these are both linear and what makes these linear. I'm going to sort of define what linear is by sort of excluding what it's not. It's not curvy, right? So these two things, this in this case a surface, and in this case a curve, these are not linear, right? I mean, you can sort of see why. They're curvy, right? This is a curve, not a line. This is a curve, not a line. These are lines. So how do we define a line? I sort of covered this a little bit before, but it's worth repeating. This is an equation that most, if not all of you, should be familiar with. You know, it's what defines a line. We have our slope, m, right, this slope, and we have our intercept, right? Yes. So what's missing here is, say, like we do f of x equals y equals, you know, same thing. So in this case, m and b are our parameters. These are the things that we're trying to learn, right? X is our input. This is variable. This is our input. We're not learning our input. We're learning these two values, these two parameters, these two weights, m and b, right? Because a line is defined by its slope and intercept. That's all the information you need to define a line. So I mean, if we look over here, this, so our slope here is like something like this, you know, rise over run. We're all familiar with that. And our intercept would be like, you know, negative 1.2 here. So I mean, I can draw it here. Say this is sort of b, you know, if you extend that, it's sort of b, and then m would be something like this, just a number that says how much this is sloping. So our goal is to find some method for letting our basically algorithm learn what the best m and b are given all of these blue data points. So we're going to be working with a little toy example today, and it's just going to be a good illustration of some of the concepts that we're learning. I've linked in the last slide a link that you can download this data and work on it for yourself. So it's a data set of cars, and there's a bunch of columns, but for now we're going to focus on two columns of the data, and those are horsepower, which is just basically how much power the engine has, and then miles per gallon, which is a measure of fuel efficiency. So basically, how far can you go given this certain amount of fuel? So we've zeroed in on these two columns here, right? And I've plotted them for you as well. So this is miles per gallon, horsepower, right? So we got all these points. Each point represents a car, right? So this point here is, say, like car. Let me draw this permanently. This is, say, car 1, right? And say it has like, this looks like 40 miles per gallon, and what's this? Maybe like 90 horsepower. Yes? So each row, I mean, this is sort of a basic thing, but it's important to get right. So each row of this sort of table here is one point over here. So one row to 1 point. Okay, so and both of them represent a car. Cool. So we're going to start off by fitting a linear regression model to this data. So that means we're going to assume that the relationship between fuel efficiency, miles per gallon, and horsepower is linear, right? So we're going to assume that it's a line. So that means our model here is going to look like some line. So maybe it looks like this, right? And you can see that this fits better than this, right? This is probably not good, right? We're trying to approximate our data using a line. So our goal, again, I'm going to repeat this because this is really important. Since we're trying to find a line, we're trying to find, what we're really finding is an m and a b, because we said that any line can be represented by m and b. So we're trying to find the m and b that best represents the line of best fit, right? So maybe it looks like something like this green thing. So how do we do this? How can we train an algorithm, or not train, but how can we enable an algorithm to learn what the best M and B is given all these blue dots, right? We want to tell it, okay, given what these blue dots are, draw a line over them that sort of fits those dots the most. How would you do that? Well, first we need a method for comparing lines, right? Like there's an infinite actually number of lines we could draw over this, right? You could draw like this, right? Like you can imagine like a big circle that you could draw lines and then, they're shifted down. You could draw an infinite number of lines in this 2D space, and we need a way to compare between them. We need a method that says this red line, say, is worse than the green one. We need some way to be like red is worse than green, right? We can see that because we have eyes. Computers don't have eyes, and we need a way to rigorously define what line is better than other lines. A loss function is how we measure correctness or wrongness of a prediction, right? We need some way to compare lines, which means we need some way to compare predictions and say, how close is our model to being correct? Okay, so this is the quick definition. It might sound a little confusing at first, but don't worry, we're gonna break it down a little bit. A loss function is any function that takes as input a labeled example from our data set, x and t. Okay, so from our car data set, we're going to talk about our specific example. Okay, if you recall, we pointed out one of the lines on that scatter plot back there. It had x equal to 90 horsepower, right? That was the x-axis, and a t of, I think it was 40 miles per gallon. Okay, so those are our x and our t, and you can imagine, that's a point, right? 90, 40 on that scatter plot. So our loss function takes this as input and our model's prediction, y, and it returns a value of how wrong our model's prediction is from the given example, right? So we're basically comparing the output of our model, which is y, to what it should be approximating, which is t, right? So a loss function really takes in t and y and outputs some measure of how close is t, or I guess it's how close is y to t. Right? And important to note, y is just equal to f of x here, where f is our model. Cool, so that's what a loss function is. Obviously, this is a very general definition. Lots of things are loss functions. And important to note is there's no one best or correct loss function, right? Like there's no, across all examples, like best one function that works for everything. You need to choose your loss based on your situation, your problem. And that's like where the art of machine learning comes in. So let's think about what we want to use for our car problem, right? So like what makes a prediction good about this? So let's draw a line, first of all. Nice red line. Let's say it's, it's a pretty good fit, but maybe it's not the best one, right? So how do we know whether a prediction is good or not? So let's call, we're going to do y equals f of x, right? And we have all these labeled examples. We have, well, it's probably not going to be the best color. So let's take a look at a couple of these. Let's highlight a couple of these. We're going to look at this one. We're going to look at these three examples. Actually, let's look at these two and say one here. Okay. So how do we measure the difference? So we have y values, right? So this red line is all of our y values, and then these greens are x's and t's. So just right off the bat, we can see that these two are pretty far off the line, right? Like, keep in mind that we want t to basically be equal to y. That's what we want, right? This t here, this t, and this is y for this one example. So let's call this example 1. This is t1 and y1. Okay, these are very far apart. Compared to, let's call this example 2. Right, compared to this t is t2, and this y is y2. These are pretty close, right? So we need some way to compare this. Obvious way to do it is let's just subtract t from y, right? So let's just say y minus t. Are we done? Not quite. We have an issue here. If we take a look at, say, point 3 now, this is going to be point 3. This distance between t and y, if we do y minus t, what is that going to be? Positive or negative? That's going to be positive, right? Because y is larger than t. So this is going to be a positive difference, okay? Compared to point 1, let me change colors to make it consistent here. Compared to point 1, this is going to be a negative difference, right? Because y is less than t, and we're doing y minus t. That's going to be negative. Do we want those to be opposite, right? Like, do we want something that's below the line to be one sign, and something that's above the line to be a different sign? Think about that. Does that make sense? If we're trying to measure correctness, aren't those approximately the same amount of correct for our example? Like, do we care if something's above the line or below the line? Don't we really just care how close it is to the line? Okay, so we could do one thing to remedy that. And this is not wrong. This is just not what we're going to do today. You could put absolute value signs, right? Because then both of these would be positive. The y minus t for 1 and the y minus t for 3 would both be positive, right? If we do absolute value. This is not what we're doing today. What we're doing today instead is we're going to square this, right? Which does the same thing, right? Like, squared y minus t is still always greater than 0, greater than or equal to 0, right? But the key thing that it does is it punishes things that are further away from the line much more than things that are close to the line, right? Instead of it scaling linearly, where like y minus t, if something's 10 away from the line, it's punished, say, like 10, and then something's 100 away from the line, that's, say, punished 100, right? That would be linear. Here, this makes that quadratic, right? So if something's 10 away from the line, and say that's like 10, if something's 100 away from the line, then that would be like, in the thousands of punishment, which is what we want. We want to more severely punish things that are further away. Things that are closer, things that are close, that's fine. That's a pretty good approximation. We're okay with that. We're less okay with things being way off. So that leads us to the first loss function we're going to talk about today, which is called squared error loss, and that's what we just sort of defined. It's like an extremely common loss choice for regression. It's like, as you saw, it's pretty natural to arrive here. Just another term. I know there's a lot of terms today, but I promise they'll solidify themselves soon. Y minus t is called the residual. That's a term that people use sometimes. Since this is squared, we sort of talked about this already, but since this is squared, it penalizes over predictions as well as under predictions, and penalizes them at the same rate, right? Like, if something's above the line, something below the line, they're both treated the same amount of wrong, right? If they're the same distance away. It's really a measure of distance. Additionally, since it's squared, it punishes more incorrect predictions more severely, right? So that's the thing, like instead of using absolute value, which would be like a linear punishment scale, we're punishing things on a quadratic scale. A cost function, another new term, cost function, not complicated, is the average loss over the entire training set, right? So squared error loss, this is for one training example, let's not even call it training example, one example from our data set. You could think of that 1 point, right? Notice mean squared error cost, not complicated. It looks sort of complicated. All it is it's taking the squared error and taking the average. It's summing over all the training examples, or all of those points you saw, and taking the average squared error loss. So this is average over all points, okay? Not complicated. It's just, think about it this way. The reason why we're doing this is to compare lines. And to compare lines, you don't want to just compare by single examples. You want to compare over all of the examples. Just to hammer this point home, if we take a look at this again, maybe I'll clean this up a little bit. If we want to compare lines, say we only compared using loss, say we only compared given, say, a single point, right? Both of these lines would be equal if we're only considering this point, right? If we're only considering loss at that 1 point, both of those lines would be equal, and it doesn't, they're clear. Both of those lines are clearly not good fits for this data. However, if we're comparing cost, which is the average over all of those, right? There's only one good line, and it's somewhere like this, because we're taking into account all of these distances for all of these points. Yes? That's why we use cost. So again, cost is just the average loss over all of the training set. So now we run into another problem, right? So we have a good way to compare lines, right? So that's what loss and cost are for. Cost is the average of all of the losses over all of the points. So we can compare lines. So if we have two lines, we can say, oh, this line has less cost than this. That means it's a better fit for our data. We have that. The issue is it's still an infinite number of lines we could draw, right? And we know this because both m and b can be any real number, right? So that there's an infinite number of pairs of real numbers. So now the question becomes, how do we find the best, right? We can't just draw it like I just did. We can't just draw that and say that's the best, because we're thinking algorithmically. This has to work for all examples. We're not going to be able to see it. Humans aren't doing this. So we need to define a rigorous method for updating m and b to minimize cost, right? So we're talking about gradient descent now. Gradient descent is sort of a big topic and trips a lot of people up, but it's really not that complicated. And we're going to try to explain it in the simplest way today, so you can really think about it in an intuitive manner. So gradient descent is how a model learns the best parameters, and I'll put, slash weights. So how do we know we found the best line? So hypothetically, we're thinking in terms of cost now, right? So we know that the best line has the least amount of cost, right? Because it's the closest fit, which means that all of those residuals are the smallest given our squared error. So how do we know that we found that? Well, we have this cost measure, and cost takes in, well, let's think about this for a second. It takes in t, right? It also takes in y, okay, and y is defined as mx plus b, right? So really, we could rewrite this as cost takes in t, m, and b, right? We can even simplify this further. Actually, t is a constant. right? T can be thought of as a vector of the target values. So like T for example 0, T for example 1, T for example 2, right? We have all of those Y values in that scatter plot. We can just bundle it all in a vector and it's constant. So now cost really only takes in M and B, right? Cost takes in the line and tells us, okay, how good is this line over our training examples? So how do we think about this? We want to minimize this, which means we want to find the M and B that minimize cost. So now we're going to start visualizing cost in terms of a surface, right? So let me get rid of these. These are wrong. This is M, this is B. J, see this like little J thing? That's cost. Okay, we can rewrite this cost of M and B. Okay, so this might look complicated, or I know I didn't really understand this the first time I saw it, but it's not complicated, right? So we have this base down here, this plane. Let's focus on this bottom plane, right? Which are the space of all M's and B's, right? So we have each point on this plane is an M and a B, right? So this this point could be something like -15, -15, M equals -15, B equals -15, right? Yeah, so that's not that complicated. And then cost, which is our third dimension here, can be just thought of as the costs associated with that M and B. So the way I like to think about this, and you can let me know if this is helpful, is all points on this plane are all of the lines that we could possibly draw, right? This plane really exists, it expands in all directions infinitely, right? We're focusing on this place because this is obviously a place of interest. So any point on this represents a line, and then you just project it up you add basically the cost of that line, and then you get the surface, right? So what we're visualizing here is the cost surface. It's often called a loss curve, but it really is a cost curve of all of the lines in our problem. So if you were looking at this, how do you minimize cost? How do you find the point that minimizes cost? Well, it's hiding right there, right? It's obviously right there. It's at the bottom of this little valley, right? And all we have to do is go like, okay, yep, that's M, that's B, check. Machine learning mastery. Well, not so fast. We don't have all of these points. We don't have all these values. This is a visualization of what exists, right? But in order to get this surface, what do you have to do? You have to try all of the values. So we're not making our problem better. Our problem is that we have an infinite number of lines to try to find the minimum cost. And this is not fixing our problem because this is just a visualization and we've plotted all of these points. So we still have to calculate all of these. We don't want that. We want to do it without calculating. And that's where gradient descent comes in. So we're going to do a little thought experiment to do this before we introduce maybe the mathematical definition of gradient descent. So say you're plopped down somewhere on this surface, okay? You're going to exist here. This is where you are, okay? And you're blindfolded. You cannot see anything around you. This is a key point. You're blindfolded. Can't see. Oh no, you can't see. Okay, the only thing you can feel is the slope beneath your feet. You can tell which way is downhill, and you want to get to the bottom of this hill and find a nice valley. You want to just chill out in the valley, and you want to get down to the bottom of it. And this is not a very tricky thought experiment to solve, but how do you get down to the valley, right? Using the fact that you can feel the slope of the ground underneath your feet, which means you can go in the direction that's down in that instantaneous point. So like if you're here, you feel, okay, this way is down here, right? If you were here, you'd feel, oh, this way is down here. Okay, if you were here, you'd be like, oh, that way is down. Okay, you can feel that. Okay, what do? You just take steps downward, right? So say you start off here, erase these. You feel this, okay, down, and then you're here, and you say, oh, which way's down? You go this way. And eventually you land in your happy valley, and now you're blue because you're happy. Okay, and then you found the bottom. Okay, well that's gradient descent. That's all it is. It's basically like, okay, take where you are now. We're somewhere on this curve, somewhere on the surface. We have some initial M0, B0 value here. And we're like, okay, what's the direction down? Walk in that direction. Take a step in that direction. And then iterate. Do that until we find some bottom. That's gradient descent. So we're going to do the mathematical definition now. It looks scary. It's really not. It's not more complicated than what we just talked about. So gradient descent is defined as an iterative method for finding an optimum set of parameters relative to a model, loss function, and training data set. Gradient descent uses the gradient of the given cost function, which is the average of the loss, to minimize it over the training set. Okay, so we have these two sort of equations here. They're declarations, basically. We're updating. These are updates. Okay, it's basically saying that, I mean, we're going to break this down a little bit more here, but just know that like this is m and b at I plus 1, right? So that's iteration I plus 1. So say this is run for 9 times. We're trying to figure out the 10th, the ith plus 1. So I is 9. We're trying to figure out the 10th m and b. So we're just taking steps down this hill, right? This is I equals 0. This one's I equals 1, right? And so on and so on. We're updating m and b, and we're updating them based on the previous m and b. So mi and bi, and then we're subtracting this weird math stuff here. Okay, and we're going to talk about what that is in a second. Hint, hint, it's the gradient. So we're going to start off with the sort of formal math definition of what the gradient is. That the gradient is this little triangle thing, upside down triangle thing that you're seeing over here. So the gradient of a function, I can write this here, say f, is equal to the vector of the partial derivatives of the input of that function. So it's sort of the partial of f with respect to, say, x1, partial of f with respect to x2, and so on and so on. That's not important for understanding what gradient descent is. What is important is understanding that the gradient of a function at a certain point is the direction of steepest ascent on the function at that point. So what does that mean? You already know one gradient pretty intuitively, I'm guessing. So say we have a parabola here. And we want to find sort of what the gradient is at that point, okay? It's the direction of steepest ascent. It's this direction. The direction of the gradient is the direction of steepest ascent. And that's called the derivative when you do it in a one-dimensional curve. That's the derivative. What that would correlate to is that the derivative is positive, right? So you know going in the positive x direction will increase the function. And that's true. Okay, so now imagine this was a surface instead. So I'm going to go back to our surface here so I can sort of show you. Imagine this is a surface instead. The gradient, say at this point here, is the direction of steepest ascent, right? So it's going that way, right? So the gradient, I'm going to do another one just so you can see it better. So the gradient at this point of the function, you can think of as going this way, right? So it's moving in this plane direction down here, such that this function increases the fastest, the steep direction of steepest ascent. You can think about it as the gradient is the feeling underneath your feet back in that thought experiment, which tells you the slope of the hill that you're standing on, right? So it tells you which way is up and down. So if you imagine your feet are on this hill, if your eyes were closed, you could feel, this way's down, this way's up. The gradient is the direction of up, the direction that takes you up the fastest. So if we do -1 times the gradient, it's the direction of steepest descent, which is the thing we wanted, if you remember. We want to go down the hill. as fast as possible. So how do we update our parameters given this information? Okay, we're going to sort of walk through gradient descent from another perspective here. So key thing to understand here is that this plot on the right is the same thing as this plot on the left, except we've squished the cost dimension down, and we've sort of represented them as these circles, these ellipses, so we can look at it in 2 dimensions. Okay, sort of the colors are, I tried to make them like match as much as possible. So what we're looking for is we want to step down these circles as fast as possible, right? So if we're here, we want to go this, right? And we want to go like that. Okay. So let's take a look at this M update first. So I'm going to reiterate what we covered on a couple slides ago. So we're taking the previous value of M and we're subtracting the gradient times alpha, and we're going to talk about alpha in a second. Alpha is called the learning rate, and it's sort of going to define what the step size we take is, but that's not important for now. What is important is saying that we're taking M and B and we're subtracting the direction of greatest ascent from the previous value, right? So we can represent this as a vector actually. So let's do M, B, and this is going to be I plus 1. Right? And that's going to equal MBI minus alpha times the gradient of the cost of MIBI. Okay, so what does that mean? So MBI, let's plot that. So MB on the ith iteration. So let's say we're here. Say we're initialized at, say, I equals 0. This is MB0. Okay, and we want to know what MB1 is going to be. So we're going to take the gradient of MBI. So that is going to be the direction of steepest ascent, which is that direction, right? Because I would go uphill the fastest. Maybe it's a little curved this way, straight like that. Okay, and we're going to subtract that, right? So that means we're going to go subtract, so times -1, this direction, directly in the opposite direction, which is the direction of steepest descent. That checks out. We thought that that was going to be the case. That's good. So we're going to subtract this direction, which means we're adding this direction. Remember, subtracting this, we're going to add this, right? And that's going to take us to MB1. Cool, and you can imagine this repeating, so let's do it again. What's the direction of steepest ascent? This way, right? What's the direction of steepest descent? This way, so we're going to add that, read it here, MB2, right? And you can see that if we keep doing this, we're going to end up somewhere in this lower circle, and we're going to stop when there's nowhere more down to go, right? And that's where the learning rate comes in, because if you imagine, so we're imagining like we're in this valley here. What if we step over the valley? So say this is the absolute minimum point here. What if our next update takes us over this, right? Because this is all sort of equal, so it would really go through it. It would go like this. Oh, okay, what do I do now? Steepest descent, this. Okay, we'd never get down to this minimum value. We just keep stepping over it. And that's where the learning rate comes in. So the learning rate, alpha, if it's too small, right, we'll just step slowly. And we don't want to step too slowly because we don't want to wait forever. If it's too large, we'll oscillate over the minimum, right? Like we'll never be able to get down here because our steps are too big, right? So good learning rates are learning rates that are somewhere in between here. And there's stuff called learning rate decay, in which the learning rate gets smaller the closer, the further in training you get. We're not going to talk about that now. But just know the learning rate is sort of the step size you take during gradient descent. Now moving to sort of like the world of concrete code, in sklearn, it's really easy to fit a linear regression model. You just use this module called linear regression from linear models. You define it as an instance here called regression model. Then we're going to do regression model.fit. We're going to pass it our training data. So really, these are not y trained, these are really t's, right? These are our t's and these are our x's. And we're fitting our model, so we're basically having it run gradient descent and find our coefficients m and b, and that's going to be our train model. So that's how you do it here. We're gonna go over this in more detail in the lab. And this is what comes out when we train this, right? So this is great. This looks like a good line. This is sort of like the lines I was drawing before, which means that the computer is definitely learning something. It looks like it fits it well, right? And we have this testing cost, right? So I just had it print this out, which is 19.78. So that's our cost for our linear regression on this data. Can we do better though? I'd say yeah. So we're going to expand on linear regression now. We're going to talk about things beyond the quote line of best fit, right? So we're going to talk about multivariate regression, which is using more than one input feature. More on that next. Talk about polynomial regression, fitting curves. Not everything's a line, some things are curves. And we're going to talk about logistic regression, which is classifying. Okay. So multivariate linear regression, we can use more than one input feature. So instead of a line, we're fitting a plane, right? If we're using two input features, it is a plane. If we're using more than two, they're hyperplanes. That's what they're called. So they're just in 4 dimensions. The only change here from our univariate linear regression is that we just have more parameters to learn. So in the 2D case, look over here, we have W2, W1, and B instead of M and B, right? So we've added an extra one. I've changed M to be W1 so we can sort of add on to them using just the 2. Okay, so W means weight here. And then for D input features, it looks like this, right? It's just the sum of WD, which is, say, one of these. So this is W2, W1, we could have W3. So WD times XD, which is your input dimension. And then we're adding B still, our intercept. Make sense? Nothing fancy here. We're just adding more parameters. So going to our example, say we're gonna add a new input dimension of model year, so the year that the car was released. This is what the plot looks like, the scatter plot now, right? So we have points in 3 dimensions now. Remember, each row here corresponds to 1 point here. In sklearn to fit here, we're just going to have x. Difference here is x is going to have model year in it now rather than just horsepower. And what we get is this nice plane here, look at that, that goes through all of our points, sort of wonky to visualize, but it's here. And the plane has basically learned, like the model's learned a W2, W1, and a B, right? Notice our plane obtains a better cost than our line. Our line was 19.78, this is 15.15, okay? And you can think about some conclusions to draw from this. For instance, if you imagine, I mean, we can talk about this in the office hour on Saturday, but can this plane equal the line that we found before? Like during training, couldn't this model have been equal to the line? Like couldn't it have settled on the line that we had found in just our linear regression? And I would assert yes. All it would have to do is set W2 equal to 0, and then you just have our initial thing, and it could be W1 equals M and B equals B from before, right? And that means that this plane is at minimum as good as our line. Because it has the expressivity, which we're going to talk about a little later. It has the ability to be the line we found before, which was the optimum solution for just one variable. This plane has the ability to basically be as good as that at a minimum. So which means we should expect a better cost here. So that's one of the conclusions. You can think about some more and talk to me about it in office hours. Important to note here, very important to note, no matter how many input features we have, our prediction remains uncurvy, right? We're still linear here. These x values are still raised to the power of 1. They're still linear. No curves, straight. It's a plane. It's straight. It's a linear relationship. That's about to change, though. Polynomial regression. This is how we fit curves, right? Not every relationship in the real world is linear. In fact, few relationships in the real world are linear. We can represent any polynomial by the following here, right? Where m is the max degree of our polynomial. So like, say we set, I'm just going to give you an example. Say we set m equal to 2, which would be a quadratic, right? F of x, and this is univariate, right? We have one input dimension, right? So if m were equal to 2, f of x would be w2 x squared plus w1x plus w0, which, you know, we're used to calling b, just the intercept. Yeah, so that'd be a quadratic. Note, you can fit any quadratic here with w2, w1, w0, 0. This has the expressivity of any quadratic curve, which means that this has the expressivity of any polynomial. And we fit this the exact same way we fit a line. We're just optimizing these weights to minimize the mean squared error cost, right? It's the same exact thing. We're using gradient descent to step down that curve. And looking back at our 1D car example, this does not look like a line. I mean, I sort of said in the beginning, oh, let's fit a line to this and did this, but it doesn't really look like a line. Using our eyes, we can sort of see that this sort of looks like a curve, right? That fits much better than this. Right, so let's try to fit a quadratic to this. This is the result of fitting it using sklearn. And what it learned is this green line, and this green line looks really good. This looks like it fits the data really well. And even look at this, we have this testing set cost, which is lower than the other two we've gotten before, which is interesting. These are the sort of 3 weights that it's learned. I just put these here to illustrate that all it's learning is these 3 values, right? This curve is represented by those 3 values completely. So comparing, so we're gonna like, what kind of like general lessons can we learn here for like training models in the real world? So we've done 3 models so far. We've done like a univariate linear regression here, right? And we had a cost of 19.78. We did a multivariate linear regression here, and we had a cost of 15.15. That was a plane. And then we did a univariate polynomial regression, which was a curve in one dimension, and we got 14.15, and that's lower than both of these, right? So what we can draw from this is just 2 strategies so far for improving model performance, right? We can give our model more data. So that was the multivariate compared to the univariate, right? We gave it an extra dimension to play with. We gave it more information so it could learn more. Or we can give our model more expressivity, basically make it more complicated, allow it to learn more things given the same amount of data. And that was the polynomial regression. So, I mean, you can sort of think something that you might want to try by yourself is, what if we combine these two? So what if we did a multivariate polynomial regression, which would look like some curvy surface in this 3-dimensional space? So I've been talking about this concept called expressivity a lot, and it's a really, really, really key concept in machine learning. We're going to continue to talk about it next week and the week after, but I wanted to introduce it here because like with these simple models, it's really easy to understand. So we have recall we have this polynomial regression formula here, and I've plotted, say, this green line is the real world underlining pattern. This is the thing that if our model fits it, it's perfect, it's great, right? Green is real world. We can call this, say, the real world distribution. Okay, and we have these blue points. Those are our training points. And this red is our model. Just, f of x. Okay, so we want our red to match our green, basically. And you can see here this m1, that's the max degree of the polynomial we're fitting. So if m equals 1, we're just doing linear regression, right? We're just fitting a line. And obviously that does not fit super well, right? M3 looks like it fits pretty well. Out of these three, M3 is modeling this distribution quite well. M9, why is it like this? This looks really bad. Well, look closely at the blue examples, the training examples. Because remember, when we're training our model, it does not see the green distribution. That green distribution is hypothetical and doesn't even really exist. We're just drawing this in this hypothetical situation. All we have are these blue points that are hypothetically sampled from this green distribution. These training points are all your model sees. So if you give it m equals 9, it matches all these points exactly. Look at the distance between the red line and these blue points. It's pretty much 0 everywhere, right? So the cost of with this m9 would be, let's say it's about 0, right? The cost for m3 is higher, right? Because you can see these blue lines, there is some distance between this red and blue points. Yes, and then you could cost for here is much greater than 0 because there's, this is not a good fit. Key point here, though, is just because this cost is lower does not mean it's a better model, because this red line is much different, much more different from the green line than this red line is, this M3. M3 is a better choice here, but why? How do we quantify that? What about M3 is better? Well, okay, so imagine we took some new examples. So I'm gonna go to the next slide so we have some clean. So imagine here on this M9, we took some new examples from our green line. So imagine now we're taking a test set and say this test set is purple, okay? Let's say we sampled this one, this one, this one, this one. Say they're a little off the line, but like they basically follow the same pattern. Okay, what is the cost for this? This is very different. This is pretty different. And this is very different. This is very different. The point is, we've taken from the same distribution, but our model does not actually approximate the distribution. It memorizes the training set. Like this model has memorized all of these blue points such that it only cares about those blue points and does not abstract out the actual distribution we want it to learn. Where if we look at M3, if I take any points, any new testing points from along this green line, they're all going to be pretty close, right? So what does this mean? This means that like if we look at the cost for M9, so let's say cost of the training, right? That's much, much less than the cost of our testing set, right? And cost of because it's memorized these blue points and gotten the cost basically down to 0, it's done that to the detriment of the model because it actually hasn't learned anything. It's just learned to memorize points. It hasn't learned what the distribution is that we're trying to learn. If this doesn't make sense now, it should definitely make sense in the coming weeks because we'll see more and more examples. Because on the side of m equals 3, the cost of training and the cost and the cost of testing are basically equal. Obviously, they're not going to be exactly equal, they're basically equal. And that's how you know that this is the better choice. And we're going to talk about how to address this to make sure that this does not happen next week. But just to recap, actually 2 terms you should know. This side is called overfitting. I mean, this is called overfitting. Right? When you memorize your training data, that's overfitting. This side is called underfitting because you really haven't learned much. Your model isn't expressive enough to learn the underlying distribution. So that's the concept of expressivity. This side is too expressive. You've given it too much expressivity so it actually can match just the exact points. It doesn't have to lose any information, it doesn't have to learn. If you don't give it enough expressivity, it can't learn the distribution that actually exists. So the goal, the hypothetical goal, is to give it the exact amount. You want to give your model the exact amount of complexity so that it can represent the underlying distribution and learn it, right? And so that's obviously not a trivial thing to do, but there are techniques for basically making sure this doesn't happen, and there's techniques for moving your model from underfitting to like a good fit. So now we're going to do the last expansion on these regression topics, and we're going to talk about logistic regression. Logistic regression is very similar to what we've been talking about, but with a sort of caveat. And we're going to be predicting discrete targets. So what is a discrete target? So we've been predicting during this lesson continuous targets. We've been predicting miles per gallon, fuel efficiency, which takes on the value of a number, right? But what if we wanted to predict something like cat or dog, or yes or no, or coffee or tea, right? So the difference here is that we've been doing a continuous target. So t has been contiguous. So t has really been in the real numbers, right? But what if t is in, say, cat, dog, right? That can only be 2 things. This is called, when t is discrete, it's called classification. When t is contiguous, it's called regression. You can sort of see here this animal regression. A regression problem would be predicting its weight, and a classification would be predicting type. So cat versus 5 kilograms. So how can we predict these discrete values? The example we're going to be using for this section is going to be, we're going to be trying to predict whether something, a drink, is coffee or tea just based on its caffeine content. So what are our input features / what is our input feature? It's caffeine content, right? We want to predict based on caffeine content. That's the only thing we want to predict on. So we have one input feature and it's caffeine content, right? And that's going to be measured in milligrams. And then what is our target? Our target is beverage type, right? What values can this take on, right? Beverage type is in coffee or tea, right? We're going to call coffee positive and tea negative. So let's first do something that's a little naive, but I think we'll see why. We're going to first just use linear regression to fit this data. So let's say we're going to plot. This is going to be coffee. This is going to be tea. This is going to be caffeine content. Right? So we can put like, say, like 100 here, 0 here, 50. Okay. So let's plot our training data. So it's going to look something like this. Say coffee. These are all coffee examples because they're plus. Okay, I'm going to say plus is coffee. Negative is tea. I'm using colors and position here just to make things extra clear. Do like that. Okay, so let's say we want to fit a line to this. So let's draw a line. What do you think fits? So let's do something like, I don't know, something like that, right? And let's call this is what we're learning. This is f of x, right? And remember, we want f of x to sort of equal t. And if we're using this some concept of loss here, this is not good. This is not good. Why? Well, this, say we'll zero in on this example here, right? The predicted value that f predicts is up here for it, right? This line continues. This is far away from this, right? So that's going to get punished. That's a high loss. Obviously, that doesn't, you know, for this line, for this thing, it's perfect. For this thing, it's perfect. But for everything else, you know, this is saying that this should be coffee with high confidence because it's well above this coffee line, right? So this is saying this should be coffee, but it's getting punished for predicting it correctly. That's not what we want. And the issue here is that we're using the wrong type of model. This just doesn't make a lot of sense. So we're going to fix it, but before we move on, I just want to introduce this concept of a threshold value. So once we draw this line, a threshold on this line would be basically drawing a dotted line, say we threshold here, saying that anything above this line is coffee. So basically anything above this is coffee. Anything below this is tea. That's just a threshold. You know, nothing complicated, but that's going to be important for a little bit later. Okay, cool. So how do we fix this problem? The problem is that highly confident correct predictions are being punished, right? So this point was predicted to be coffee with high confidence, but it's being punished because it's far away. The solution that we're going to do, it's a little trick, is we're going to squash all of our output to exist only between 0 and 1. So how do we do that? We're going to introduce a function called the logistic function. It's also known as the sigmoid function. This is it. That what it looks like is not really important. It's more of like what the plot of it looks like, right? Look at it. It's between 0 and 1. So it's between 0 and 1 for all real values, right? So as our x goes to infinity, sigma of x is going to be approach 1. Oh, whoops. Going to approach 1. And as we go to negative infinity, sigma of x is going to approach 0, right? And that's what we want. We wanted to squish our output down between 0 and 1. So let's see if we can use this for our regression. This is why it's called, spoiler alert, logistic regression, right? So in linear regression, we assumed that it was fit by a line, right? And that was our problem here. We assumed that this data was best represented by a line. That clearly wasn't true because a correct prediction resulted in a high loss, and that should never be true. So in logistic regression, we're going to assume that it's best represented by this sigmoid curve, right? So we're doing basically, look, if you look at inside here, this mx plus b looks like a line, right? It looks like our linear regression, but we're putting it inside of a sigmoid curve, which is squishing it, right? So if this was a line before, we're squishing it down. So basically it only exists where we want it to exist, because there's really no need for anything to exist outside of 0 and 1 if we're only predicting these two values of like 0 or 1 or coffee or tea, right? Like we don't care if anything's outside of here. We just want that to be 1 still. And that sort of solves our problem because we can never have something up here to have a high residual if it's correct, because it will just be squished down here and that will be like a very correct, very low loss prediction. Logistic regression is for classification, right? So for linear regression, this is sort of like a review of what's been said, but it's worth repeating. We're fitting a line. For logistic regression, we're fitting this sort of S-shaped curve, this sigmoid curve. One thing to note Here is for logistic regression, we use a different type of loss. Um, we're not going to go into the reason for that because I don't want to take up a lot more time, but just know we use a different loss and it's called cross entropy or log loss. And this is what it looks like. Looks complicated, but you can sort of look up maybe an explanation for it, or you could ask me in office hours this week and we can talk about why we use it. Yeah, this is something to ponder. And that's it. This is a logistic regression. So we're looking at this S curve and it's trained. And we have our coffee examples up here and our tea examples down here, right? So we want to classify between coffee and tea. And we're basing it on caffeine content, which is our x-axis down here. So say we sample 20 beverages and we plot them here, right? And we measure their caffeine content and we label them coffee or tea. We know whether they're coffee or tea. So this is our training data set, these red and green shapes. And we try to fit this line, right? This blue line, and that didn't really work, again, because highly correct predictions, we're having high residuals on these ends. That's what really mattered. And we don't want that. Why would a correct prediction have a bad loss score? Like that shouldn't be true. So then we were like, okay, let's squash it down and fit this S. And this S clearly matches our data and fixes that problem because it's taking all of this line and pushing it down and squishing it down here, and these have low loss and we're fixed. We're good. So the way to interpret this is actually pretty nice. It's pretty interpretable. Because we're between 0 and 1, we can sort of interpret the scores on this S curve as probabilities that it's our positive example. So what does that mean? Let's back up a little bit. So say we have one example that has an X value of 40 milligrams, right, of caffeine. And then we see where that falls on our line here, and we move that over to here, and we say this is 0.1. Okay, so what that means is it has a 10% chance that this is coffee. Does that make sense? So the score on the logistic curve, the learned curve, is basically the probability that it's coffee. Right? You could reverse that and say it's 90% probability that it's tea. Right? So this threshold, this orange value, is basically, at what probability do we say it's coffee and at what probability do we say it's tea, right? So you can move this around. Right here it's at, we're going to say it's coffee if it says a 50% probability it's coffee. And depending on your problem, you care more about classifying correct things as as positive or correct things as negative. So for example, if this was a malignant tumor classification and we were diagnosing, say, tumors based on size, right? You'd much rather have a bunch of false positives than a bunch of false negatives. Like you'd rather flag a tumor for further investigation to make sure that it's not cancer than miss a cancerous tumor and let it pass through, right? So then you'd move this threshold, in that case, down farther, so you capture more of the potentially cancerous tumors. So that's what a threshold is, and the threshold is really it's dependent on your problem. And just to finish up here, we have multivariate logistic regression, which you can extrapolate at this point. It's basically the same as multivariate linear regression with the sigmoid function strapped on the outside of it. And you update it the same way, everything's the same, still uses cross entropy loss. And that's it for their lesson today. Here are some nice references if you want to dive a little deeper into these things. Here are the contributors. Thanks to everyone who helped out with this. Good luck on the lab, and I'll see you for office hours.